Okay, welcome back. Here's the last video where we're going to go over 18.5, which talks about case control samples. So case control sampling method identifies all cases in the population from the same source population, randomly selected a series of non-cases as controls. Assertions of exposure status of cases and controls. Cross-tabulous exposure status of cases and controls. This provides an effective way to study rare outcomes. Remember I said how we have case controls. Case controls are normally done when you have a rare disease that you're particularly looking at. Because it's a rare disease, you're not going to see it a lot of times, so you have to really kind of pick these cases up, and it's a very tough type of study to do because you'll be all over potentially the world, and it's hard to really look at data when you're collecting samples from a lot of different places and a lot of different things are going on. Once again, case controls are normally done to find rare diseases. So here you have a case control sampling by incidence density method. So as cases are identified in the population at random, one or more non-cases culture each case at the time of the occurrence. So you have D's normally for disease, and this is over time. So as you define the number of occurrences over time, and then you find your new disease and long cases. This is a concept that allows students to see that case controls are a type of longitudinal study, which is another different type of study, time failure design. So you're studying particular diseases over time, and these are rare diseases. Once again, case control. So looking at cross-tabulate counts for cases and controls according to the exposure status. So here you have exposed and non-exposed and cases and controls on top. And you have your A1, B1, A2, B2, and then you have your totals for your rows and columns. And then we have our odds ratio being A1 times B2 and A2 times B1. Which remember, like I said, I think better way to do an odds ratio would be to do your A times D over B times C, which then if you do it here, A, B, C, D, it's the exact way it's set up. You'll get the same value coming out of it. And that's just the way I learned it. I think it's a little easier. Once again, do whatever is more comfortable for you. If you don't like the ABCD method for 2x2 tables, you do not have to use it. That's the way I was taught. I think it's pretty simple. It's an easier way to remember it and write it down as opposed to labeling it all correctly. And so you have here A1, here's your cross product ratios, right? This is exactly what we're doing. With incident density sampling, where the odds ratio is a direct estimate of the rate ratio in the population. So here's an illustrated example that we have. We have cases of men diagnosed with cancer, and your controls are non-cases selected at random. So you have exposure equals alcohol consumption dichotomized at 80 grams a day. Dichotomized is a fancy word saying two. So it's either they either did have 80 grams a day or they didn't have 80 grams a day. And then here's you have your cases on top and non-cases, and then you have your alcohol on the side, and so then you can calculate your odds ratio. Once again, the way they do it, you can also do it the A, B, C, D way, and you'll get the same value where you have an odds ratio of 5.64. Interpretation, the rate ratio associated with high alcohol consumption is about 5.6, which is the odds of having esophageal cancer if you consume more than 80 alcohols a day, is you are 5.6 times more likely to get esophageal cancer if you drink that much alcohol per day. If we were to do a 1 minus alpha confidence level for odds ratio, so this gets a little bit more, and you have a homework problem on it, but don't worry, it's relatively easy to set up. So here we have our formula for our odds ratio. So we have ln of the OR plus a z of 1 minus alpha over 2 times the standard error of the ln of your OR, where the standard error is equal to the square root of 1 over A1 plus 1 over B2 over 1 over A2 plus, so it's the square root of 1 over all the values you're getting. And then the note of use the natural logarithm scale. So when you use ln, that's the natural logarithm, and you can find it on your calculator. It's not necessarily more work. It's donated by the ln on the calculator. So you just type in, as you'll see here. So here we have our cases and controls, and if you do your A, B, C, D, or figure out your odds ratio is going to be 5.64 like we calculated. And if you just, on your calculator, just type the ln first, and it'll give you like a quantity, and then type 5.64, and then close out your quantity, and then you'll get a value of 1.7229. That's all you have to do. You don't have to actually do ln by hand. Most even basic calculators had the ln function, natural logarithm function here, and that's where we put in our value here. So you'll see it's notated by E right down here of 1.722. That's the natural logarithm symbol, plus or minus our z of 1 minus alpha over 2. All right, that's where we get this value here. Z1 minus 1 of alpha over 2, and you get a value of 1.645, and you can find this in the previous chapters. And then the standard error, which is just the square root of all these values, 1 over all these values, and you have your value here. And then it's very similar to just how our other confidence intervals have worked. You multiply these values out, this is what you're going to get, plus or minus, and then you state your natural logarithm at the very end, and there you go. And that's your confidence interval. It's not too much more. I think the crazy part is just seeing the ln and knowing that then you're taking it for these other values. But it's the same steps that we have been doing for confidence intervals. So it shouldn't be too much of a hard question to answer on the homework. And that's why I threw all this in here so you could see kind of the math worked out for you. And I know the chapter goes a little bit deeper, but for purposes right now, this is all we're going to cover. I mean, it is kind of 3 brand new formulas and understanding what they are and how they apply to different types of observational designs. So we have our relative risk, our odds ratio, and then we have chi-square as our test of association, which is also called the fitness of good test. So we have all these different things, and I think that's a pretty good way to end the semester here. Once again, if you always have questions or comments or something doesn't make sense,